Now we're going to take a look at collisions between objects whose paths are defined by parametric equations. That's gotta hurt. So here we have actually two sets of parametric equations, and so we're dealing with two objects in this case. And the goal here is to see, first of all, what paths they each take, and more importantly, do those paths lead them to collide, to run into each other? And if you think about a collision, what is a collision? It's basically when two objects are at the same place at the same time. And so we have both of those things in our parametric equations. In other words, we have the same time by looking at the value of t, and we can have the same place by looking at the coordinates x, y. So here we have the two sets of equations, and we'll go ahead and fill in the values. And so if we plug in the values of t, 0, 1, 2, 3, we'll go ahead and get the values that are shown in these two tables that describe the paths for both objects. And if we go ahead and plot the paths of the two objects over here at the particular times, t equals 0, 1, 2, and 3 for the red, 0, 1, 2, and 3 for the blue, we can see a couple of things. First of all, we can see that their paths cross, which means that they are both at the same point sometime in their travels. Now the question is, are they there at the same time? And we can look at the values in the table here with respect to time and see that their paths cross, but they cross at different times. The red object is crossing at t equals 1, which is sooner than the blue object, which is not crossing until t equals 2. And so therefore these two objects will not collide, even though they're going to be crossing paths. This time we're going to change one set of parametric equations, and it turns out that if you were to eliminate the parameter on this and the previous set that we just looked at, you would find that they actually lie on the same line. In other words, their paths are going to be the same. Now the question is, will they occupy the same point at the same time? Now that we look at the values and we look at the paths on the graph, now we can see that both of these objects will be crossing paths at the same time. In other words, t equals 2, t equals 2. At that time, both objects will be at the point 0, 1, and therefore they collide. Let's go back over to the tables and take a look. At time t equals 2, we have times equal. So in other words, we can say that, let me get a pen here. We can say that t equals 2 in both cases. And then we want to look at what is happening to the position. The position is 0, 1 in both cases. And so we say the position, xy, is 0, 1 in both cases. And what does that mean? Same place, same time, and that is a collision. Let's compare that with the previous case here. If we take a look at our first example, we had t equals 2 and t equals 2. We had different positions. We had 0, 1 in the case of the blue, negative 1, 3 in the case of the red. When were they at the same place? Well, if we look at 0, 1, they were both at 0, 1, but at different times, t equals 1 and t equals 2. And so these objects did not collide. They were at the same point somewhere in their individual travels, but not at the same time. In the case of these two objects, they were both at the same place and at the same time. So, how can we test for collisions by looking at the parametric equations? What we're going to do is we're going to set both of the x of t equations, one for the one set and one for the other set, equal to each other and solve for t. And so what that's going to do is tell us at what time t that their horizontal positions are the same. So if x of t of one object and x of t of the other object are equal at the same time t, then their horizontal positions are the same. Now, just because their horizontal positions are the same does not mean that they collide. What we need is both their horizontal and their vertical positions to be the same. So we're going to take that value of t that tells us when their x values are the same and plug that into both of the y equations. Now we'll find out what the vertical position is for each point when their horizontal positions are the same. If their y values are the same, then both the horizontal and the vertical positions are the same. Basically, they're at the same place at the same time, and we have a collision. If the y values are not the same, then they're not colliding. Now you notice we could also start by setting the y values, the y equations rather, equal to each other, solve for t, and then plug that in to test the x equations. Sometimes one way is easier to do than the other. So let's take a look at these two sets of parametric equations and see about the collision. We've got a simulation set up over here, and so I'll just go ahead and start that, and we can see what happens. So it looks like they're heading maybe to where their paths are going to cross. The question is, do they cross at the same time? And the answer is yes, it looks like that they did. So how can we verify that for sure? Well, let's go ahead back to our process here, and what we're going to do is to try to find out, first of all, when are they at the same x value and the same y value, and we can do this in any order. In this case, I've actually got a pretty simple expression for y in this case, so I'm going to start by setting the y equations equal to each other. So I want y1 of t equals to y2 of t, and that's going to tell me what value of t are my y positions going to be the same. So for y1 I just have t, and for y2 I have 2t minus 3, and I'm going to solve this for t. Let's subtract t from both sides, and then we'll add 3 to both sides, and that gives me t equals 3. So the y values are the same when t is equal to 3. The question is, what about the x values? If the x values are also the same, then we know that both of them are at the same x and y, and we have a collision. Otherwise, they're not. So we're just going to take these two x expressions here and plug in t equals 3. So x1 at time 3 is going to be at position 2 times 3 minus 2. This is 6 minus 2. x1 will be 4. And then we'll do the same thing with x2 at time 3. That's going to be equal to time 3 plus 1, which is 4. And so both objects then are going to be at the same y position, or the same xy position at time 3. So if we went back and plugged in t equals 3, we would see that y1 equals 3, y2 equals 2 times 3, which is 6, minus 3 is also 3. So at t equals 3, they are both at 4, 3. And if we go back to the demo and take a look, we can see that at 4 and 3 seems to be where they crossed, and it turns out that that was at the same time, t equals 3. Let's see if we can set that back to exactly t equals 3, and we can see that they are at the same point, 4, 3, 4, and 3. Okay, let's see if we can predict the behavior of these two objects following these parametric equations. Since I have the squared up here, I'm going to leave that for second. I'm going to go ahead and set the y expressions equal to each other. 2t equals 5t minus 3. I'm going to subtract 2t from both sides, and then I'll add 3 to both sides, and then divide by 3, and I get t is equal to 1. So their y positions are the same when t is equal to 1. In fact, if I plug them in, I'll see that y1 of 1 is equal to 2 times 1, which is 2, and y2 at time 1 is going to be 5 times 1, which is 5, minus 3, which is also 2. So now let's take t equals 1 and plug it into our x values. x1 of time 1 is going to be equal to 1 squared plus 1, and that's going to give us a value of 2. T equals 1 in this expression for x2 is going to give us 1 plus 3 is 4. So at t equals 1, the positions are object 1 is at position 2, 2, and object 2 is at position 4, 2, and therefore they do not collide. So let's take a look at the simulation, and we'll go ahead and start that, and we can see that indeed those two objects do not collide, even though their paths do cross. What about these two guys? Let's go ahead and compare them. Once again, I have a squared up here, so I'm going to start with the y's. I'm going to take t plus 2, set that equal to 3t minus 2, and let's start off by subtracting t from both sides, and then we'll go ahead and add 2 to both sides, and then divide by 2, and we see that t equals 2 is when their y values are the same. And we'll just go ahead and see what the y values are. When t equals 2, y sub 1 is 2 plus 2 is 4, and so we would expect y2 when t equals 2 to be 4 as well. We have 2 times 3 is 6 minus 2, and that's equal to 4. So let's take our value of t at 2 and plug that into the x equations. For x1 at time 2, we have 2 squared is 4 plus 1 is 5. And for x2 at time 2, we have t equals 2 plus 3 is also 5. And so both objects are at the position of 5, 4 at t equals 1. And we should have a collision in this case. So let's go ahead and take a look at the simulation. So these are following the same path as before, but now they're actually meeting each other at the same time. And again, that time gives us a position of x equals 5 and y equals 4. So to review the process for testing for collisions, the first thing is to set both of the x equations equal to each other and solve for t. This tells you when their horizontal positions are the same. Take that value of t and plug it into both of the y equations. You get two numbers for those. If those two values are the same and the two x values are the same, then the objects will collide at that time t. Otherwise, they don't collide. And again, we can start with the y equations, find when the y values are the same, and then test the x equations. Sometimes one way is easier, as we saw in the examples.